Welcome to Brain Vision.
Received based on the skin as shown in figure 42. Typical sound wave frequencies of about 5 megahertz are used, which have a reasonable chance of being reflected from red blood cells. By measuring the frequency of the reflected waves, which are Doppler-shifted because the red blood cells are moving, the speed of the detected. Normal blood flow speed is about 0.1 meters per second. Suppose that an artery is partially constricted so that the speed of the blood flow is increased, and the flow meter used a Doppler shift or measures a Doppler shift of 780 hertz. What is the speed of the region? The effective angle between the sound wave, both transmitted and reflective, and the direction of the blood flow is 45 degrees. Assume the velocity of sound in the tissue is 1,540 meters per second. So I wrote down some things that we were given here. The speed of sound, C, is 1,540 meters per second. The velocity of the blood flow, I call V times B prime, is equal to the cosine 45 degrees times V of B, which is the velocity of the blood. So this is the blood flow relative. Cosine 45 degrees was that angle. Well, cosine 45 is 1 over root 2. So this is 1 over root 2 V sub B. We're also told that the frequency emitted is 5 megahertz, which is 5.0 times 10 to the 6 hertz, and that the Doppler shift, which is going to be that frequency minus F double prime D, which is the frequency detected, is 780 hertz. Okay, so the first thing we're going to do is measure the frequency relative to the blood flow, which is F prime B. The first thing we're going to do is going to calculate that, because that ratio is equal to F times 1 minus 1 over V sub B prime, right? V sub B prime, which is the relative blood flow divided by the speed of sound. Okay. Well, then F double prime D, because that's really wanting to find is the detected frequency. F double prime D is equal to, because this is going to be the opposite of the direction of the blood flow, is going to be equal to F prime B divided or times 1 over, which is the same as divided by 1 plus V sub B prime divided by C. Okay, so that means that if we plug in our V sub B prime that we just found in the previous equation, that F double prime D is equal to F times 1 minus V prime B over C divided by 1 plus V prime B over C, right? Well, we'll just multiply through by C. So that's going to be multiplied by C minus V prime B divided by C plus V prime B. Okay, well, what we're trying to figure out is the velocity of the blood flow, right? So first, let's solve for V prime B is equal to, solving this equation, F minus F double prime D divided by F double prime D plus F. Okay, well, V prime B is 1 over root 2 VB. So that means that the velocity of the blood multiplied both sides by root 2 is equal to root 2 times F minus F double prime sub D over F plus, or F double prime sub D plus F. Okay. Oh, I also forgot to multiply this by C. Don't forget to multiply all of this, of course, by C, because we have this C here, which I just going to underline. I just underlined it, both of those places. Okay, so then this also needs to be multiplied by C, of course. All right, well, up top, which I'm going to mark by a little green star, we have F double prime D and its relationship to the Doppler shift, which we know. And it's also related to F, which we know. So let's go ahead and plug in the fact that F double prime D, which to the side, solving that star equation. So I'm going to write it in green. F double prime D is equal to F minus 780 hertz. Okay, so we can plug that in to our equation for VB prime, or I'm sorry, for V sub B, the velocity of the blood, and we find that velocity of the blood is equal to root 2 times 780 hertz on the top. The reason being, if we go back to the previous page, we plugged in for F double prime D, we plugged in F minus 780. So F minus F, the F's cancel, and then minus 780, minus a negative is a positive. So we end up with just 780 hertz. And then we do the same thing for the bottom, but this is F double prime D plus F. So we end up with 2F, the F's add, and this is going to be minus 780 hertz. Okay, and then again, everything here multiplied by c, the speed of sound. So we have everything in this equation that we need. We plug in for F, 5.0 times 10 to the 6 hertz, and we plug in for C, 140 meters per second. We find the velocity of the blood flow is 0.17 meters per second in the restricted artery. And we find that that indeed has from 0.1 meters per second in unrestricted. Box that in is our solution.